Where did everything come from?
How did we get where we are now?
Where do humans fit in?
Where are things heading?
These are the questions that are going to be answered throughout this documentary.
There are 8 major thresholds, all starting from the Big Bang up until the modern revolution.
If these events within these chapters had not occurred at just the right times that they did, then there would be no time, no space, no planets, no life. So in other words, there would be nothing.
Each chapter played a key role in where we were, where we are now, and where we will be.
This is our universe.
We're going to be talking about the Big Bang.
Before the Big Bang, there was no time, no gravity, and absolutely no human life. There was nothing.
We don't know much about what existed before the Big Bang. The only thing we know for sure is that it happened about 13.7 to 13.8 billion years ago and created the building blocks of everything that we have today.
Some scientists believe that for this to occur, the universe had to enlarge rapidly, which then caused it to explode. Now, the universe is still expanding up until this very second, minute, and hour of history.
We do not know much about the ingredients or Goldilocks conditions that led up to the Big Bang, because there's almost no evidence. For example, what made the Big Bang possible? We have no clue. Why did the Big Bang happen? That's only speculation. Was there even space and time before the Big Bang? We can't say for sure. History teacher Garrett O'Sullivan about a few questions about the Big Bang. Firstly, which of the many theories that surround the Big Bang do you agree with the most?
I don't necessarily agree with any of them. Everything in the big history course is about evidence, and frankly we have no idea what happened before the Big Bang. Everything that happened before that, we speculate, we guess. There's one theory I particularly like, which is a multiverse theory, which means that our universe is just one of an infinite number of universes floating around out there in space. And a universe is created then, a new universe is created when 2 of these multiverses collide with each other, creating a new third kind of daughter universe. And that's what the Big Bang was, the collision of two universes, 2 of our multiverses that eventually created a new universe, completely new one. That's a theory, there's no evidence of it. We have some small evidence, things like dark energy and dark matter, which we don't understand. They point to things like this, but these are completely theories. And I think that's the wonderful thing about a course like the Big Bang and this idea that we're always learning. We understand the limits of our knowledge, we don't know, and we're okay with admitting that. We just don't know.
Yeah, that's an interesting theory.
Yeah, it's very interesting. There's lots of them. There's lots of them out there. That's one of my favorite ones, though.
Yeah. Okay, so describe in detail what you think the first few moments after the Big Bang were like.
Extremely hot, extremely violent, and extremely dense. The universe would have heated within about 1 second. It would have heated up to about 10 billion degrees Kelvin within the first second after the Big Bang. It would have been a dense ball of like matter and energy in that first second as well. And they estimate about 10,000 times denser than the stone you can see around you out there. So the universe was extremely hot, extremely dense in that first second, and it expanded very, very quickly. And then since that time, after that first second, ever since then, it's just slowly expanding further and further and further out, and cooling all the time. To about, for example, within about 300 years, it cooled down to about 1,000 degrees Kelvin. So it's just constantly cooling. But the first few seconds after the Big Bang was very violent, very, very hot, and from that point onwards now, the universe is just slowly expanding and cooling at all time.
After the Big Bang, the universe cooled down, setting the stage for the new threshold to take place, the lighting up of stars. When evenly distributed particles with equal gravity are disturbed by a nearby object, the gravity of one becomes greater than the rest. This particle draws in more and more matter and collapses onto itself, starting to rotate and flatten into a disk. This disk, at 10 million degrees Celsius, goes through nuclear fusion, leaving a bright new star to light up the universe.
This was caused by slight variations in the distance between evenly distributed particles. This caused two atoms to come closer together, meaning that their gravitational pull is stronger than particles around them. This eventually led to the formation of stars.
Chemical equations for thresholds consist of ingredients and Goldilocks conditions to produce new complexities. For this threshold, we need hydrogen and helium atoms and gravity. Or Goldilocks conditions consist of tiny variations in density and temperatures higher than 10 million degrees Celsius to produce our new complexity, stars. Not only did stars like our Sun come from this threshold, but so did galaxies like the Milky Way, clusters like the Virgo cluster, and superclusters like the Virgo supercluster.
Gravity is a fundamental force that acts on every different object in the universe. And stars are formed in nebulas, and nebulas are a collection of gas and dust. Nuclear fusion is the principle of is when two atoms join together to create a heavier atom. In particular, in stars, small stars and stars in the main sequence fuse hydrogen into helium.
Today we're here with Miss Henrietta Levitt. Good morning, Miss Levitt.
Good morning.
So I was wondering if you could tell us a little bit about your discoveries.
I'm mostly known for the law I discovered, called Levitt's Law. When I studied Seyfert variables, these are large stars that pulsate at regular intervals. That is where, after some time, I noticed a relationship between a star's brightness and its frequency of pulsation. The brighter a Seyfert variable, the brighter it pulsates.
Oh, that's interesting. And how does this exactly link to the stars lighting up in big history?
Well, without knowing the distance between stars, we wouldn't have noticed the change is increasing, suggesting that the universe is expanding. This is something that helped develop the theory of the Big Bang. But without stars, we wouldn't be able to measure the distance, because there wouldn't be any light reaching us.
Oh, okay, but that's very interesting. Thank you, Miss Levitt.
No problem. No problem. No.
With the lighting of stars came the next threshold in our big history story, the creation of new chemical elements. The heaviest elements are created in the bellies of aging and dying stars. Once the star reaches the end of its life cycle, it will explode in a massive explosion called a supernova. It's at this point that all the new chemical elements, the complex elements that make up you and me, came to be dispersed throughout the universe. We are all made of stardust. The new complexity which emerged from this threshold is astonishing. All the elements which can be found in the periodic table were created by stars. All the beauty and complexity of chemistry and the interactions between elements came to be at this threshold. Without stars going through their life cycles, starting at nebulae, advancing to protostars, to a main sequence stage like our Sun, and finally to a fiery death in a supernova explosion. The chemistry necessary for life simply wouldn't exist without the natural life cycle of a star.
The cause of this threshold was from the forming of stars. New chemical elements will constantly form inside the star. Then, when the star dies off, all the new chemical elements are released out into space.
The most versatile element, probably I would say, is carbon, because it has so many applications in so many different areas of all our lives. We use it from drugs in medicine to other kinds of compounds. It's used it's present in everybody and everything around you practically. It also carbon forms millions and millions of different compounds. So many of them useful, many of them effective, maybe not in a useful way, but many of them active. New elements, not very many new elements. Well, you can't predict a new element. It's either there or it's not there. We've either discovered it or we haven't discovered it yet. There are some gaps in the periodic table, but those are of elements that have not been discovered. But having said that, they have made a few elements, and elements are formed, or what makes an element unique is its nucleus. So they can either add to or take away from the nucleus to create an element.
Thank you. Okay, and just a bonus question.
Oh, lucky me, a bonus question.
Okay, so Mrs. Watkins, do you trust atoms?
Not very much. They make up everything.
Okay, thank you.
And I'm Luisa.
And we're going to be talking about the fourth threshold, which is the Earth and the solar system.
Clouds of matter spin around and around our young sun, slowly forming just about everything in our solar system. From asteroids and meteors to all the planets and moons, one planet in particular, Earth, would enable the creation of even more unique complexity.
Whenever someone talks about leftovers, we usually find it not that gratifying. However, in this case, the leftovers that surrounded the sun were more than gratifying. They were very important. The leftovers fell into the sun, while others were decimated by the gravitational pull. Gravity helped separate matter by density, forming all of the planets, including one of which we get to call Earth.
Our planet Earth was perfectly positioned at just the right distance away from the sun and composed of diverse elements. This then generated the perfect spot for the perfect conditions, or Goldilocks conditions, for increasing greater complexity.
It is our sun and everything that travels around it. Our solar system is elliptical in shape. That means it is shaped like an egg. The sun is in the center of our solar system. Our solar system is always in motion. 8 known planets and their moons, along with comets, asteroids, and other space objects, orbit the sun. The sun is the biggest object in our solar system. It contains more than 99% of our solar system's mass. Astronomers think the solar system is more than 4 billion years old. Astronomers are now finding new objects far, far from the sun.
We interview our big history teacher, Garrett O'Sullivan. So for question 1, can you explain the process in which the Earth formed?
Absolutely. In a couple of our previous chapters, we talked about how the sun was formed, and our sun was no different. At the center of our solar system, a sun formed. And when it ignited, there was a massive explosion which sent the lighter gassy materials out to the outside edge of our solar system. And the heavier rocky materials remained in around the center and started circulating around our sun. Over time, in a process called accretion, these rocks and stones that are full of rich minerals, they started to clump together under the force of gravity. And over a long period of time, millions of years, these began to form planets. It takes a huge amount of time, and it's all done under the force of gravity, dragging together lumps that are rock that are bigger and closer together, but then they'll start to form up together into larger planetesimals, for example, first, and then they go into nodule, and then finally they'll become a full planet. Okay?
That's very interesting. So, going along with that, how did Earth gain a moon? How did we have a moon?
That's something that there's still a lot of discussion about that. The most recent theory in relation to it, and it can't be proven 100%, but they're quite certain on it. The most recent theory is that there was two of these planets, these forming planets circulating around our sun, and at some point they had this massive collision. The planet that hit us, they estimate to be about the size of Mars nowadays, so it's a big, big collision. The entire Earth was turned into molten rock after the collision from the sheer force of it, and a huge amount of material then was thrown out into the orbit around the Earth as a result of the collision. And that material, in exactly the same way that the planets formed circulating the sun, that material started to coalesce together under the process of accretion, circulating or orbiting around our planet. Ultimately, that formed our moon, which circulates around, which is hugely important because it's stabilized. The moon is used to stabilize our rotation, for example, our orbit, and plays a huge role in the formation of life on Earth.
Interesting. And along with the first question, why is it so important that Earth has so many diverse minerals inside of it?
This is one of the weird things about our universe, and one of the things that are more difficult to understand. Why, for example, if you go to the overall universe, everything that you can see out there, about 98% of everything is either hydrogen or helium. It makes up 98% of what exists out there in our universe. However, on planet Earth, if you look just at the crust of planet Earth, about 65-70% is made up of two things like oxygen and silicon. So why is planet Earth's makeup so different than what the rest of the universe is? We best understand it that at that moment in time when our sun ignited, and they expect that our sun is going through a third life cycle, so it produced some very, very heavy elements and very heavy materials when it was forming, and it started to spit out all of these new materials. The rocky, heavier materials, they're harder to blow away in the explosion, so they stayed closer to the sun. The lighter, gassy materials were blown right out to the edge of the universe, or the solar system. That's why you get the gassy planets at the outside and the rocky planets on the inside. And obviously a rocky planet would have more chemical diversity within it. And so that's how planet Earth came to have all of these different chemicals and elements. And everything that we build around us today, from the computer chips that we put in our computers, they're all made from these elements that are sitting in our Earth's crusts. So it's hugely important that we have this planet that's got a lot of diversity of minerals in it.
All right. Thank you.
No problem at all.
What is life?
To live.
Life is how you perceive the world. and yourself.
Earth had the perfect Goldilocks conditions for life to form. This includes having the crucial elements for life like carbon, hydrogen, and oxygen, which are formed in dying stars. Another Goldilocks condition is just the right amount of energy. And finally, the presence of liquid water. Liquid water had slow-moving atoms, making it easier to combine into more complex molecules. The perfect place for life to form is in oceanic vents, which are cracks in the Earth's crust, letting the heat and elements from the mantle into the water, allowing the formation of different molecules which then create forms of life, or organisms. We can trace the formation of these organisms back to the last universal common ancestor, also known as LUCA. LUCA is a single-celled organism which lived about 3.5 billion years ago. All living organisms today have evolved from LUCA. Organisms can live up to 2 kilometers above Earth's surface and 11 kilometers below sea level, but humans and most of life can be found in a thin layer called the biosphere, also known as life's comfort zone. Life in the biosphere has been subject to many drastic and dangerous changes, occasionally resulting in mass extinction. Astronomy, biology, and geology have a huge role to play in the shaping of the biosphere into what it is today. One way in which life affects the biosphere is by changing the atmosphere. During the early beginnings of life, plants started to photosynthesize, taking carbon dioxide out of the air and putting oxygen into it. This change in the biosphere actually led to a mass extinction because at the time, oxygen was poisonous to most organisms on planet Earth. This is called the oxygen holocaust. This mass extinction paved the way for eukaryotes, what we are, to evolve.
Humans have really evolved over time. Collective learning and the ability to share what we learn separates us from other animals.
Humans are very similar to other animals, but what makes us different is our ability to share information in different ways. The development of speech and writing boosted our ability to share information and spread ideas. Evidence that shows collective learning is the making of stone tools. In different parts around the world, the same stone tools were made, indicating that early humans told others about their ideas and shared how they made them. How they did this was by communicating with each other through early forms of writing. In conclusion, due to powerful brains, precise symbolic language, and interactions between both communities and individuals, there are new ways in which we can connect and adapt our environment without genetically changing, and we can also pass information from generation to generation. Agriculture was important because it meant that people no longer needed to move around and could stay in one place, leading to civilizations, villages, and cities, and that meant that collective learning could accelerate. Foraging was simple and easy. So why switch to agriculture, and how? Now you may assume that there's a simple explanation as to how we switched from foraging to agriculture, which is someone had the idea. But it's not that simple. There are 5 steps to explain the switch. 1. Humans already had the knowledge and skills for farming. They understood animals and understood the anatomy of plants. 2. There were specific plants and animals that were well suited for domestication. 3. Humans in some regions became less nomadic after the last ice age. They settled down in regions of local abundance, and foragers could stay in one place due to warmer and wetter conditions that were suitable for farming. Populations increased, and there was more population pressure. The trap of sedentism. Population growth made it impossible for foraging to sustain increasingly large communities. They had to find new ways of living, and farming became the only option. 5. The commitment to farming. This theory works everywhere. In China, Mesoamerica, Southwest Asia, and Egypt,
It all makes sense. Irrigation is the redirection of running water to aid farming. It was used in areas with little to no rainfall in suitable amounts for farming. This was important because humans could now farm land that they couldn't before. Agriculture led to collective learning because humans no longer needed to move around, so they could stay in one place and share information easily, which led to building pyramids, garden walls, civilizations, and rise in new technologies and advancements in how they moved things around.
Threshold 8 began about 200 years ago, and we're living in the middle of it. We call it the modern revolution because it created the world we live in today. Some geologists call the modern era the Anthropocene. That's the era in which the Earth came to be dominated by a single species, us. How did we suddenly get to be so powerful?
In 1950, a new source of energy was discovered. Fossil fuels, including coal, oil, and natural gas. Fossil fuels are made of dead plant and animal matter buried underground for hundreds of millions of years. These fuels were then extracted, providing cheaper, more efficient energy source. This all took place because they used wood as a main resource of construction, as well as cooking and cleaning. But alas, their precious trees started to run out. They had to revert to a different method, coal. When they were extracting the coal ore, they ran into a problem which left them dumbfounded for some time. The dilemma being that the coal mines were filling with water, and buckets and their other methods of removing the water were futile. This slowed down the collection of coal until an inventor, James Watt, invented a stable, sustainable solution, the steam engine. This allowed water to be pumped out of the mine at a faster pace. This all led to the chain of innovations with different inventions being made, each problem being fixed with a new acceleration in technology. And hence the unofficial geological era where humans have a large influence over the biosphere, which is the surface and atmosphere of the Earth. An example of this is the Industrial Revolution. During the Industrial Revolution, factories started to emerge around London. These factories used heavy machinery and ended up polluting the air and surrounding cities. On the other hand, the Industrial Revolution was the beginning of machines doing difficult and dangerous jobs instead of people. Also in this time, inventions like the steam engine allowed people to spread and share ideas faster, creating more interconnected populations. Imperialism, the main cause of the Industrial Revolution. Imperialism is when a country that has a specific ruler, such as a king in that day or time, would take over a different country to exploit them for goods. For example, wood. They ran out of wood rapidly because it was the main source of energy. Rulers would decide to go to a different country and take the goods that they required by force, leaving the country that they exploited for their goods at a loss. The demand of the goods produced was too large for the merchants at the time, so they required many laborers in their establishments. But as they started to produce machines to do the same thing as the laborers, but faster, they decided that they didn't need as many laborers, making the people lose their jobs as they were not needed anymore. So for the merchants to make work easier, instead of using many people that they had to pay, they decided to use less people and to utilize machines, which then sparked innovation.
Learning collectively was a new thing that was able to allow the spread of ideas through countries and different counties. As new experiments were done as new products were invented, the news was spread quite rapidly, and here's why. The modern revolution, basically how it is today, has produced such ample amounts of technological ways of sharing ideas, as well as important information for the destruction or the development of countries. These ideas caused the diffusion, shout out to Dr. B, of different religious, godly figures and different perspectives on our origin and how we came to be.
Because of rapid interconnection, war and conflict are initiated quicker and more frequently than ever before. For the majority of history, wars would begin because the everyday working-class population started asking big questions like, this person isn't a good ruler, why are they king? Or this person doesn't believe in the same things I do, why are they on the same bus as me? These questions, interconnection, and people that felt the same way started to band together. And where this happened on large scales, there was soon revolution. A good example of this is the Civil War in the USA.
the working class people, slaves, started to ask why they were treated so badly and why none of them were rich plantation owners. These questions were asked, and the people that believed in the same thing band together, and a social revolution began, resulting in the Civil War. Different world zones shared goods, beliefs, ideas, diseases.
With a rapidly growing population, more Nepal is being used. This is filling our atmosphere with carbon dioxide and other harmful emissions. What these emissions do is create a blanket by the ozone layer, trapping heat, steadily increasing the planet's global temperature. This can be harmful in many ways to our climate, environment, and the human race. Yet we do not have to worry about these consequences, as there has been a solution to this dire situation. Renewable energy sources have made a huge positive impact on global warming by creating an efficient and eco-friendly source of electricity. Renewable energy is an energy source that is not depleted when used, for example, wind and solar energy. If we increase the amount of renewable energy used, this would allow us to replace carbon-intensive energy sources and reduce global warming.
Even though all of these advancements have greatly impacted our ways of living, there was one big advancement, the space race. This was a race between the United States of America and Russia to see who could achieve the milestone of traveling to the moon first. They tested and failed many rocket launches before the USA was successful with one launch. This sparked a new technological revolution of space exploration. This furthered our understanding of the planet in which we inhabit and the galaxy surrounding us.
From nothing to something. Our story began 13.8 billion years ago with the Big Bang. The whole cosmos made in an instant. From the creation of the first star to the astounding explosion of the first supernova that created and spread the building blocks for everything we know today. These events, through the right ingredients and Goldilocks conditions, led to the formation of our Earth, our solar system, and inexplicably, us. With the help of time, we evolved, adapting to our changing environment. With our enlarged brains as Homo sapiens, we were able to start accumulating and sharing knowledge. The methods of sharing and accumulating knowledge for future generations became more efficient through writing and drawing. As a result of collective learning, we found that we didn't have to migrate and instead could settle in one place by growing our own food through agricultural practices that improved over time. These small settlements were able to sustain a larger population, eventually growing into towns and cities, leading to the modern revolution, our latest threshold. Each of these 8 thresholds have been unique, wondrous, particular, precise, unpredictable. What the future holds, we do not know. What we do know is that we have an eternal connection with the universe, one that can't be broken, for it is everything that is known and unknown, everything that we are and are yet to become, because we came from the universe, and the universe is in us. We are Star Sun.